Hi there, welcome back to Calculus of Variations. In this video we're going to look at something called the Jacobi test. Very similar to Legendre test but with added extra. Okay, now as a reminder, on the last video we derived the second variation and we put it into a simpler form, and I'll just write that down now, where we had I2, the second variation. It was the epsilon squared upon 2 factorial, the integral from a to b, okay, of f11 times eta derivative minus eta u derivative upon u all by dx. Okay, and the Legendre test really told us that if we had the first variation 0, which was the Euler-Lagrange of partial f by partial y minus d by dx of partial f upon partial y derivative equals 0, okay, and also if the differential f11 maintained the same sign over the interval AB, okay, and in this instance here, that's squared actually, in this instance here, if we had to ensure that that doesn't equal 0, okay, so we would have to say eta derivative minus eta u derivative upon u didn't equal 0, because if it equaled 0 then the whole of the second derivative would equal 0. Then you would have to look at the third derivative in order to find the value for the sign of this, and the third derivative would have a epsilon cube term in it, so it means that the cube term in the third derivative would mean that the value of this I2 would be dependent on the sign of epsilon, okay, and we don't want that, we want it only depend on the sign of f11. So then you would have to go to the fourth derivative, and we really don't want that, that's just too difficult. We want to simplify it. So if these are the case, then we can say that f11, if f11 is greater than 0, then the extremum is a minimum, and if f11 is less than 0, the extremum is a max. Okay, now that is the Legendre test. In the Jacobi test that we're going to look at, we're assuming 1 and 2, okay. Now in this 3, we're actually going to look and see the conditions under which we can ensure that eta will ensure that this here doesn't equal 0. Okay, so we're really looking at this, but we're just adding in the extra section saying we want to make sure this doesn't equal 0, and this is how you're going to do it. Okay, so what they do is, if we assume that this does equal 0, then you would have eta derivative minus eta u derivative upon u. Okay, now if that equaled 0, then what we could do is we could look at this as its own little differential equation, and we could say we're choosing values of eta, okay, and we want to make sure we choose a value of eta that ensures that this doesn't equal 0. So, well, we want to find out the values of eta that would make this 0. So the solution to that would be eta of x would equal some alpha u of x, okay. So it's really telling us that this would be 0 if the u of x is a multiple of eta of x. This is just some simple constant. Okay, so what we want to do then is we can show that is true if we just put in alpha u of x into that. So I'll just do that. So you're going to end up with alpha u derivative of x minus alpha u of x times the u derivative of x all upon u of x. Now all of that would have to equal 0 if that is the solution, and you can see that's the case because the u of x would cancel with the u of x there, and then you would just add, you would have alpha u derivative of x minus alpha u derivative of x, so all that would cancel out and the whole thing would end up being 0. Okay, so this tells us something quite interesting, and it points away to an extra test that would ensure that this value doesn't equal 0. So what we could do is we know that, I'll just draw it quickly, we know that if we draw, I'll put it in a different colour. Okay, if we were to draw in our u of x, okay, let's say there's a u of x there, u of x there, okay, then we know that if this value eta of x is some value lambda times u of x, so let's say eta of x comes up like that, okay, and it comes down like that, and it lands at the same point, and we know that if each of these points here is just a constant coefficient times constant number times the other point here, okay, then we could pretend then in that instance there, this value here would equal 0. Okay, so in that lies a solution. What we want to say is one of the solutions that we have is that we'll choose our value eta of x so that it doesn't cross this point here. Okay, it crosses somewhere else on this line. Okay, now there's three options we're going to have. We're going to have u of x, and I'll just draw them in here quickly. So u of x will cross, if that's A, and we call that B. Now let's call the point it crosses A dash. Okay, so we could have it passing crossing the point at A dash, where A dash is within that interval AB, and we could have it passing there outside that interval, okay, A dash, or we could have it passing actually on B. Now we don't want it passing on B, we already know that. Okay, so in each of these instances we could put 1. Now if we say, now, and then another thing, these points here, they're given a very specific name, they're called conjugate points. Okay, so remember that in each of these instances here, we're going to be multiplying this by some value epsilon to get a family of curves. Now the one thing that the family of curves has in common here, in this instance here for that one, is that they all pass at this point here and pass at that point there, and these are conjugate points. Now the same would be said for a family of curves like this. The conjugate point would be a load of curves and each of them would pass at that point. Okay, so you equally say the roots of them will be the conjugate points. Okay, so what we could do is we could look at this and we could say if B, right, equaled the conjugate point A dash, then we don't want that to happen because we would end up with this being 0 and the second variation being 0, so we don't want that to happen. Right, now number 2 is if the value of the conjugate point A dash if conjugate point actually lies within our interval AB, okay, so there's our interval AB, or could you actually could better just write in terms of and say that in this instance here B would be greater than A dash, okay, so the B is a greater value than A dash, so A dash is within this interval. Now if it's within that interval, it could have a value there that's an integer multiple, okay, but then outside that it has a value 0. Now we're not going to cover that, we'll put a question mark there, because we're not going to cover that in this course, okay, it's a more advanced topic and we'll maybe cover it at some other point, okay, so we're just not covering that, okay, and in fact the Jacobi test is a test to ensure that we just don't go there, okay. Now the third option is that B is less than A conjugate. Now in that case here, this is this one here, okay, so it means that we could potentially have a value for u of x which is some constant a constant difference from our value of eta of x, okay, over the interval a b, but you notice when we get to b, there's no way when we get to b at that point there that you can make the u of x, you can't write u of x times some alpha equaling eta of x. You can't write that at this point here because u of x is 0, okay, so there's absolutely nothing that you can multiply alpha by to get this eta of x, okay, so that there is the extra test, the extra thing we're going to be adding, okay, which makes this the Jacobi test, okay. So really the Jacobi test was going to be one, that we have a the first figuration is 0, and 2, the f11 doesn't change its sign over AB. I'll mention that in another video. If it changed its sign over AB, it means that we'd be able to choose a value of eta that would determine whether this is positive or negative, and we don't want to be able to do that. I'll mention that when we come to talk about our conjugate points, okay. And this value this here is going to be true, but it's going to be made true if we ensure that the fourth point is true, and it's that the conjugate point, okay, that the conjugate point of our eta of x, so let's write this down, eta of x, our conjugate point is greater than b, okay, so it's really just telling us that we want to make sure that this point here lands outside of the interval AB and not inside and not on B, okay, so that's all there is here for this, and we're working through the rest of the sections assuming that the Jacobi test is satisfied. Now on the next video I'm going to talk about conjugate points. We're going to look at a bit more about them and some of the useful ideas and things that can help us with. Okay, thank you for listening and goodbye.